In the last screencast, we looked at the basics of heaps. Now we want to use our heap to do something useful, namely to sort some elements. And the first order of business is to construct the heap. So unlike with a priority queue, many of the applications of priority queue, here we're going to start with a large number of elements that we want to put in the heap initially. And so it's going to be important to come up with an efficient way to do heap construction. So the most obvious thing to do for most people is, well, let's just insert the elements one at a time. This is called top-down heap construction. And you'll see, you should try to think through why this is theta of n log n in terms of its worst case performance. The basic idea, but you need to justify this, is that if you think of the elements that are going to be placed into the heap, there's going to be n of them. Once the heap is constructed, half of those elements are going to be leaves, basically, or approximately half, and half of them will be internal nodes. And when you think about putting in the last n over 2 elements, the last half of them, they're going to be at that bottom level of the heap. Okay, so there's going to be n over 2 of those, and in the worst case, each one of those elements that's inserted is going to have to drift up all the way to the root. And that's going to take log of n over 2 operations. And since there are n over 2 of these elements, well, you can go from there to hopefully be able to see why the worst case performance is going to be theta of n log n. But there's a better type of construction, namely bottom-up heap construction. And in this case, we initialize the heap's array structure with the keys just in the order in which they're given. We don't worry about, all we worry about is getting the structure property here. We're not worried about getting the heap property. So once we've entered all the keys into the array, what do? Well, now we have to get the heap property back. And the way we do that is we start from the bottom of the heap and take the last node that has children. Okay, that'll be the node that has index n over 2. And we take that node and we see if we try to make what's below it into a heap. And so we do a drift down. So in other words, if the node doesn't satisfy the heap conditions relative to its children and descendants, then we drift it down. It turns out, and then we go to the previous node in the heap and do drift down on it. And we work our way all the way back to the root, and we work drift down on the root. It turns out, and I'm not going to prove this, that this will enforce the heap condition on every node, in every parent node in the heap. And this is exactly what we want. That makes the entire array now into a binary heap. The worst case performance on this, it turns out to be theta of n. So it's much better than theta of n log n. It's a little bit harder to prove. The one way to think about it is that now half the elements are not going to have to move at all in terms of doing the drift down operation. And then the ones where most of the elements are at the bottom of the binary tree, the essentially complete binary tree, and those don't have very far to go. Whereas the only one with a long way to go is now at the root. At any rate, that's just a hand-wavy justification for why the performance is theta of n. So as we've seen, bottom-up heap construction is more efficient than top-down heap construction. So on this slide, I'm just going to do an example where we do bottom-up heap construction on a very small list of numbers. So here are the numbers, 2, 9, 7, 6, 5, 8. And what we're going to do, notice, is all we do is insert those into the array in the order in which they're given. So the 2 goes in the root, then 9 goes to its left child, 7, etc. Okay, so now we have the structure property satisfied, but we do not have the heap property. So we start with the parent node that's furthest down the tree and to the right, that's 7, and we compare it with 8, and we see when we compare it with 8 that the its child is bigger than 7, so we swap them, and we come over to this representation, where now the 8 and the 7 are correct relative to one another. The next thing we do is we go and look at the next parent, going backwards up the tree, and that'll be 9. We compare the two children, 6 and 5. 6 is greater than 5, and then we compare 9 with the 6, and lo and behold, 9 is greater than 6, so we don't need to do anything. Then finally, we go to the 2, the root, and we look at its children, 9 and 8. 9 is the greater one, and so we swap the 9 and the 2 in the positions, okay? And then we look at 2 and see if it's in its correct spot yet. So we compare its children. The 6 is bigger than the 5, and 6 is bigger than 2, so we swap the 6 with the 2, and we end up with this array. Representation is represented here as a binary tree. And what do we find? We find that that's a heap. Notice 9 is bigger than its children, 6 is bigger than its children, and 8 is bigger than its child. Here's some pseudocode for the bottom-up heap construction. I'm not going to spend a lot of time on this. You can look at it. You've already seen drift down in detail. This is a slightly different version of drift down, but here's the key portion that's different than what we've seen before. This is the actual going through the vertices on the binary tree, starting with the first parent, okay, in terms of being furthest down the tree and furthest to the right. And we loop, as we go through this loop, we move down to the root, which is 1. Now that we know how to build the binary heap for a large array of numbers, let's talk about how we do heap sort. So the first thing we do is we construct it for the given list of things that we want to sort, for the n things. And then what do? We do source root, we remove the root n minus 1 times. Now, the way we do this is, it turns out we can be clever and not have to use a lot of extra space. We remove the root, and basically what we do is exchange the key that's in the root with the last rightmost leaf that's in the heap. Okay, and we decrease the heap size by 1. So if in a max heap, we'll be putting the max element at the last position in the heap, in what was the heap. And then we need to restore the heap property, of course. So we do a drift down on the key that we've put into the root in terms from this swap up here. And we just do that n minus 1 times. So think about what's going to happen. The first time through this loop, you're going to put the largest element in the heap at the end. And the next time through the loop, you're going to put the second largest element from the original heap in the next spot, etc., etc. So you're going to end up with the entries in the array. If you do this in place, what used to be the heap is now going to be a sorted array of the elements. So you may or may not want to do this in place in terms of the original heap. You might actually want to make a copy of the heap. It depends on the kind of application you're going to do. But if the application is purely just to do a sort, you can do it in place, and the array that you construct will then be an array of the elements in ascending order, if it was a max heap. And the only thing you need to be careful of is now that those elements begin with index 1 and end at index n. So when you return the array, you need to be a little bit careful. So here's a little example to illustrate what's going on. It works on takes our previous example, and here's the heap construction. We start out, we put our elements 2, 9, 7, 6, 5, 8 into the array, and now we have to enforce the heap property. So we compare 7 with its child 8. 8 is bigger, so we do the swap. Then we check 9 against its children, which are 9 is in spot 2, so we look at slot 4 and 5. And 9 is bigger than 6 and 5, so we don't need to do anything. That's okay. I should have been pointing here. And then we go down and we look at 2. We compare 2 with 9 and 8. 9 is bigger than 8, so we swap the 2 and the 9. Okay. And so now we have 2 in this spot. We compare it with its children, which are the 6 and the 5. 6 is bigger, so we now move the 6 back where the 2 is and move 2 down to here. And now 2 is a leaf node, so we don't need to go any further. So we end up with this heap. Okay, so now we've constructed the heap, and now we do the root / max removal and reorder the array. So here we're going to take 9, we know it's the maximum element, so we swap it with the last entry in the heap. So we put the 9 there, 7 there. Okay, then we have to restore the heap property. Okay, so we compare the 7 with the 6 and the 8. 8 is bigger, so we move that there, and the 7 comes over here. Okay, and then we need to check the 7 against its children, but it doesn't have any children, so we don't need to worry about that. So then we remove the 8 and swap it with the 5. Okay, put the 5 here. 5, we have to check 5 against its children, 6 and 7. 7 is bigger than 5, so we move the 7, swap the 7 and the 5, and now we're ready to go again. So now we remove the 7, which is the max, put it there. Swapped it with the 2, so 2 is there. We have to compare 2 with its children, 6 and 5. 6 is the largest child, so we swap the 2 and the 6. And now 6 is the largest element, so we swap the 6 with the last element, 5. So now we have 5 and 2. We compare 5 with its child. 5 is fine, so we don't need to do any swapping. Now so that's indicated here where we didn't do any swaps. So then we take 5, which is the largest element, and put it and swap it with the 2. And then since 2 is the last, is the last element, we're all done. And so now you'll see we've got this array in ascending order. So when you do this with a max heap and do the sorting in place, then you get an ascending order for the array. If you wanted the descending order array, you could just move through the indices in the reverse order. So that's it. That's how heap sort works. If we analyze the performance of heap sort, the building stage, right, we already analyzed that. That's theta of n, so that's fast, that's linear in n. And then the removal, we have to do that n minus 1 times. And the key thing, the work comes in, is in fixing up the heap. And what's the worst case of that going to be? Well, we're going to have to do that roughly n times, okay? And we have to do the drift down operation, and that's, in its worst case, is going to take log n. So it turns out that this is going to be theta of n log n in terms of the actual sorting aspect using heap in place. So it turns out both the worst case and the average case efficiency are theta of n log n. So this was a pretty quick trip through heaps and heap sort. I strongly encourage you to find a text, either the text we're using in class or one of the other reference books that I gave you, and read through them to make sure you understand the details of how all this works. Good luck, and thanks very much.